So it is not often that I actually have to print out the numbers 1 through 100 and then actually use them for something, right? Normally I just teach how to do that. But here we're actually going to do that to play a game that that you may have played before. All right, and the game is fairly simple. It is, I am thinking of a number from 1 to 100, right? Guess a number, and I will tell you whether it's higher or lower, right? So I'm thinking of a secret number. Let me go ahead and, I will go ahead and grab a piece of paper, for theatric's sake, and write it down, right? And just show you how this algorithm works, right? You've probably played this game as a child, right? So I've written down a number, and if you guess the number, yay. If you don't guess the number, then I'm going to tell you whether it was higher or lower. Your guess, or you should go lower or you should go higher, right? So now there is, so let's think of the simple strategy, right? If there's unlimited guesses, then then really what I could do is say, is it 1? Is it 2? Is it 3? Is it 4? Is it 5? Is it 6? Is it 7? Until, they get sick of us just blabbing at them. And eventually we'll get our answer, right? That is linear search. But if you've played this game before, then you probably know there is a much better position to start with. And it's to ask, for simplicity's sake, I'll just say, hey, is the number 50, right? And so depending on whether it's higher or lower, I'll tell you higher or lower. And I'll say it's higher. So why is this a good move? Well, since you know it is 50, since you know that this is higher than 50, it must be somewhere from 51 to 100. And that means that we can cut that out right there. We can go from 100 numbers to a grand total of 50 numbers, right? The lines over here are just for the number of numbers we have right now. And here's the actual numbers. So now, after this, you might need a bit of math, but you're like, oh, there's 50 numbers. So we wanted to basically choose the middle number. So 75 seems like a good number. Is the number higher? And you say, is it 75? Right? And why do we choose 75? Well, if it's higher, then you know that if it's higher, then you have these 24 numbers to deal with. Sorry, if your number is lower than 75, you have these 24 numbers to deal with. If it's higher than 25, you've got these numbers over here to deal with. So it is, in fact, higher, which means that we know not only is it not lower than 75, it's also not 75. If it was 75, I would have told you so. And now you're dealing with 25 numbers. So 2 moves, by the way. We've made 2 guesses so far. And we shrank from having to search between from 100 numbers to 50 numbers to 25 numbers. On the other hand, had we been doing the linear search, is it 1? Is it 2? Is it 3? We would have shrank our search space from 100 to 99 to 98. So in 2 moves, we've gone down to a quarter of the search space. And now you ask, let's go ahead and continue this, right? Find the middle number, right? It's a bit hard when you've got 25, but let's grab it and say, hey, 13, right? Is our number 88? Our number is not 88. The number we're looking for is lower, so we cut out these numbers, and we are now looking for 12 numbers. Okay, let's go and look at the number in the middle now, right? Because if we choose the number in the middle, then we basically are eliminating half the search space each time by knowing that basically, oh, it can't be lower or it can't be higher, right? So let's go ahead and say 81. It's less than 81, so we're going to cut out these 6 numbers over here, right? And notice that, it really doesn't matter too much so long as it's pretty much close to half over here. So we'll be more exact when we actually come up with an algorithm for this. And so now we shrank it again. Is it less than 78? Yes, it is. And let's see, 76 or 77. Is it 77? No, that didn't work so well. Hey, but it is, in fact, 77. So what does this have to do with logarithms or logarithmic runtime and binary search in general? Well, this exact same process is how it's going to work in binary search, and this is an example of a logarithmic algorithm. So let's just simply get it out of the way of what a logarithmic algorithm is. O log of n. So first off, when you see log in the computer science context, we're talking log base 2. Okay? Not base 10, base 2 in computer science. In fact, we often have a special symbol for it, right? Just like ln is natural log, and log you might assume is log base 10. In computer science, you can assume that that is, that is base 2. LG, though, we often use for just base 2. That pretty much always means base 2. Although, I should mention, though, that in terms of big O, we really don't care what big O, what base the logarithmic time has. We just really don't. It's not too much we have to worry about, and we can just assume, for the sake of argument, it's base 2. And also, base 2 makes our explanation that we're coming up with much simpler. Log base, so I'll just simply assume again log, this is log base 2 of n. What does that mean? Now, this is the explanation I wish I had gotten for what a logarithm is, because, right, if we look on the Wikipedia page for logarithms, mathematics is the inverse function of exponentiation, right? Because my mind totally works like that, right? Using that equations and stuff, but honestly, and it's got this weird properties and stuff, but it is actually a lot easier explanation than for that. And the explanation I like to use, and this is really only good for integers, right? So log base 2 of n is the number of times I can take n and split it into 2 piles recursively. And what do I mean by that? Well, let's take log base 2 of 64. Now, we should know that basically that, right, 64 is 2 times 2, so that's 4, 8, 32. So 2, 4, 8, 16, 32, 64. So that should be 6, right? Assuming I didn't completely mess up there. But that's just simply, we know that from, doing 2 to the 6th. But what I'm saying here is that that one way we can look at that is take 64, split it in half into 2 piles of 32. Then we can take we can take a pile of 32 and split it into 16. Then we can take that 16 and split it into 8s. We can take that 8th and split it into 4s, those 4s and split it into 2s, those 2s and split it into 1s. So we were able to do one split. We were able to split it up once, then twice, then 3, then 4, then 5, then 6. So we did 6 splits, right? This one doesn't count because that's where we started at, right? So one split, then each of those 32 piles could be split into piles of 16, then those 16s into piles of 8, those 8s into piles of 4, those 2s into piles, those 4s into piles of 2s, those 2s into piles of 1s. And then you can't split the 1s anymore. So that's 6 splits. So log base 2 of 64 is 6. So what log base n means is the number of times I can split it in half, right? I can split it in half how many times? Now, obviously, this does fall apart once we get to, try to calculate log base 100, right? We can take 100, split it into 50s, and split those into 25s, and the 25s into, but, 25 doesn't really go in half, but it gives you an idea of how that should work. And you'll also know that it's somewhere between 64 and 128, right? So, but this is a good enough definition. It also works for base 10, right? Log base 10 would be the number of times I can take a pile and split it into 10. I can take a number and split it into 10 piles of the same size and then keep doing that recursively. So 100, right, I can take 100 and split it into 10 tens and then take each of those 10 tens and split them into 10 ones. So that's basically the easiest way to think of logarithms. What does that mean for big O log of n? That basically means that each step we have the amount of space we have to search. Have the amount of space that we have to work with. That's what log of n means. We're basically each step we split the amount of we reduce the amount of work that we have to go through in half.